Have you ever stopped and wondered what makes your phone, your computer, pretty much everything you use every single day actually work? Well, the answer, believe it or not, comes down to this one tiny, absolutely revolutionary component. Today, we are going to pull back the curtain on one of the most important inventions in history, the transistor. And seriously, that is not an exaggeration. This little thing is the fundamental building block of our entire digital world. It's the microscopic switch, the tiny amplifier that powers everything from your smartwatch to global supercomputers. You know, understanding how this works, it's like learning the secret language of all modern tech. So, how are we going to break this all down? Simple. First, we'll get to know the transistor's two main superpowers. Then, to make things a little easier to grasp, we'll use a really simple analogy involving water. After that, we're diving deep inside the silicon itself, we'll explore the absolute magic of something called doping, and finally, we'll put all those pieces together to see this thing in action. Okay, so at its very core, a transistor does two incredible things. First, it can act as a ridiculously fast electronic switch, turning currents on and off millions, even billions of times a second, all with zero moving parts. And second, it can act as an amplifier, taking a tiny, weak signal and making it huge. So let's start with its job as a switch. Picture a basic circuit. You've got a battery and a light bulb. It's on. Simple enough. We could add a manual switch, right? But that needs a human to flip it. Now, here's where it gets really interesting. Let's swap that clunky switch for a transistor. Right away, the circuit is off. The transistor is blocking the flow. But the trick, the real genius, is when we apply a tiny electrical signal to that middle pin, the base. That little nudge acts like flipping the switch. The transistor opens the floodgates, the main current flows, and boom, the light turns on. We're now controlling a big current with a tiny one. But here's the thing. It's not just any small signal that does the job. There's a very specific threshold. Check this out. If we apply half a volt, 0.5 volts, to the base, nothing. The LED stays dark. But the moment we hit around 0.7 volts, bam, the switch is thrown, the transistor lets the current pour through, and by 0.8 volts, the gate is wide open and the LED is at full brightness. That 0.7 volt mark, remember that number. It's the key that unlocks the whole thing.
Okay, so that's the switch. But what about that second superpower I mentioned, amplification? We just saw how a small voltage can control a circuit. Well, it works with current too. Imagine our little control signal is just 1 single milliamp of current. I mean, that is a teeny, tiny amount of electrical flow.
By feeding that tiny 1 milliamp signal into the base, we can unleash a much, much larger current, let's say 100 milliamps, to flow through the main circuit. We just took our little signal and made it 100 times stronger. This right here is the basic principle behind everything from your headphones to giant stadium speakers.
And this amplification factor, it actually has a name. Engineers call it current gain, or more commonly, beta. It's just a simple ratio. You take the big current and divide it by the small controlling current. In our example, 100 milliamps divided by 1 milliamp, well, that gives us a gain of 100. This number tells you exactly how much punch that transistor has as an amplifier.
Now, just a quick heads up, there are two main flavors of these things, NPN and PNP. For an NPN, which is what we'll be focusing on, the main current and the control current both flow into the transistor. For a PNP, it's kind of the reverse. The main current flows in, but then it splits and flows out of two different pins. Don't worry too much about that for now. We're going to stick with the NPN because it's the most common.
Okay, I get it. All this talk of volts and amps can feel a little abstract. So let's try something different. Let's use a simple analogy to get a more gut feeling for what's happening. Just imagine for a second that electricity is like water flowing through pipes.
This setup is a perfect mirror for a transistor. So you've got this massive pipe with a huge amount of water ready to flow, but it's completely blocked by a valve. That's our transistor in the off state. Now, imagine we connect a tiny little side pipe to the valve's control handle. If we send just a small trickle of water through this little pipe, it's just enough to start turning the handle and opening the main valve. And get this, the more water we push through that tiny control pipe, the wider the main valve opens, letting that huge flow of water just roar through. That tiny flow is controlling the massive flow. That right there is a transistor.
The water analogy is awesome for building intuition. But now it's time for the real deal. Let's go under the hood and look at the actual physics inside that little piece of silicon that makes all of this magic happen.
I mean, this is the big question, isn't it? This is what's so mind-blowing. We're not talking about little gears or tiny levers inside. It's a solid object. So how does it do it?
Well, the secret is in the unique properties of a special class of materials called semiconductors.
Let's do a quick comparison. You've got conductors, like copper wire, where electrons can just flow freely. Easy. Then you've got insulators, like rubber, where electrons are locked down tight. They can't move. But a semiconductor like silicon, it's special. Normally, it acts like an insulator. But, and this is the key, we can control it to act like a conductor. It all comes down to how much energy an electron needs to break free. In silicon, that energy gap is really, really small. All it needs is a tiny little push.
So how do we give it that push? This is where the real genius of transistor design comes in. We use an amazing engineering trick called doping. And no, it's not what you're thinking. This is where we intentionally add tiny, microscopic impurities into the pure silicon to completely change its electrical personality.
And we can do this in two ways. First, we can add an element like phosphorus, which has an extra electron to share. This creates what we call N-type, or negative-type silicon. It's now loaded with an excess of free-roaming electrons. Or we can do the opposite. We can add an element like aluminum, which has one fewer electron. This creates P-type, or positive-type silicon. It now has a bunch of empty spots where electrons should be, and we call these empty spots holes.
Now this is where it gets brilliant. When you press a piece of N-type silicon right up against a piece of P-type silicon, something amazing happens. Some of those extra electrons on the N side immediately jump across the border to fill the empty holes on the P side. This creates a thin, neutral barrier right at the junction called the depletion region. And this barrier stops any more electrons from crossing. It creates an electrical potential, a sort of invisible wall. And the voltage of that wall? It's about 0.7 volts. Sound familiar? That's the exact voltage we needed to turn our switch on earlier.
Okay, we have all the ingredients. We've got our N-type silicon with extra electrons, we have our P-type silicon with its holes, and we have that all-important depletion barrier that forms between them. So let's do it. Let's put it all together and build our working NPN transistor.
An NPN transistor is literally a silicon sandwich. You take a really, really thin slice of that P-type material, that's our base, and you squeeze it between two layers of N-type material. One N layer, the emitter, is packed, or heavily doped, with tons of free electrons. The other N layer, the collector, is just moderately doped. This structure creates two of those depletion barriers, one on each side of the base, which means that, normally, nothing can get through. It's a double-locked door.
And here is the grand finale. First, we apply that small positive voltage, our key, more than 0.7 volts, to the P-type base. This instantly collapses that first barrier, unlocking the first door. Suddenly, a flood of electrons from the supercrowded emitter rushes into the base. But remember, the base is engineered to be incredibly thin, and it has very few holes. So these electrons pour in and have nowhere to go. They're just crowded in this tiny space. And at that exact moment, we have a large positive voltage waiting at the collector on the other side. This acts like a giant magnet, yanking all of those crowded, homeless electrons across the second barrier and out through the collector. And just like that, our tiny base signal has unleashed a massive flow of current. The switch is on.
So when you boil it all down, what is a transistor? It's a tiny, elegant, solid-state switch with absolutely no moving parts. It's just an incredible piece of material science built by carefully layering and engineering silicon to create these controllable barriers for electrons.
Think about that for a second. Every time you tap your phone screen, you are commanding literally billions of these switches to open and close. This simple, brilliant principle is what allows us to compute, to communicate, to create everything in our modern world. The transistor completely defined the 20th century, and it just makes you wonder, what's the tiny breakthrough that's going to define the 21st?